17.2 Standing waves. In this session, we will cover several key topics regarding standing waves. We will begin with the fundamental concept and the specific conditions required for their formation. This leads into a mathematical analysis of the resultant wave functions that describe these patterns. A critical part of our study involves defining nodes and antinodes, including how to determine their specific locations within a medium. Finally, we will use visual aids to understand how these standing wave patterns evolve over time, contrasting them with the traveling waves we have studied previously. Standing waves are formed when two identical waves travel in opposite directions within the same medium. A practical way to visualize this is by placing two speakers facing each other, both emitting sound of the same frequency and amplitude. As these waves overlap, they combine, according to the principle of wave interference. The most striking characteristic of a standing wave is that, unlike a traveling wave, there is no sense of motion in the direction of propagation. Instead of seeing a pulse move from left to right, we observe a steady oscillation pattern that appears to stay in one place. To represent this mathematically, we consider two transverse sinusoidal waves with the same amplitude, frequency, and wavelength. The first wave, y1, equals amplitude times the sine of kx minus omega t, traveling in the positive x direction. The second wave, y2, equals amplitude times the sine of kx plus omega t, traveling in the negative x direction. By applying the superposition principle, where the total displacement y is the sum of y1 and y2, and using trigonometric identities, we find the resultant wave function. This resultant y equals 2 times the amplitude times the sine of kx, all multiplied by the cosine of omega t. This equation describes a special kind of simple harmonic motion for every element of the medium. Within a standing wave, we identify two critical types of points: nodes and antinodes. Nodes are locations in the medium where the displacement is always zero. This occurs whenever the sine of kx term in our equation equals 0. Mathematically, these positions are found at x equals n times the wavelength divided by 2 for integer values of n starting from 0. Conversely, antinodes are points of maximum displacement, where the amplitude reaches 2 times the individual wave amplitude. These occur when the sine of kx term equals plus or minus 1, located at positions x equals n times the wavelength divided by 4 for odd integers. It is important to note that the distance between any two adjacent nodes, or two adjacent antinodes, is half a wavelength, while the distance from a node to the nearest antinode is 1/4 of a wavelength. Visualizing a standing wave helps clarify the mathematical model. In the provided photograph of a vibrating string, we can see the envelope function, which is 2 times the amplitude times the sine of kx. This envelope defines the boundaries within which each element of the string oscillates. The points where the string appears to stand still and the envelope width is 0 are the nodes. The regions where the vertical oscillation is at its widest point are the antinodes. While the entire pattern has a stationary outline, every part of the string between the nodes is moving up and down with an amplitude that depends strictly on its horizontal position x. The appearance of a standing wave changes significantly throughout one full period of oscillation, denoted as capital T. At time t equals 0, the two constituent traveling waves are in phase, resulting in maximum displacement for the elements of the medium. At time t equals 1/4 of the period, the waves have moved in such a way that they are completely out of phase. At this specific moment, every element of the medium passes through the equilibrium position, creating a flat, horizontal line with 0 displacement. By the time we reach t equals 1/2 of the period, the waves are back in phase, but the entire pattern is now inverted compared to how it looked at the start. This continuous cycle creates the characteristic jumping or breathing appearance of the standing wave. Let us look at a practical example. Suppose we have two waves where y1 equals 4.0 times the sine of 3.0 x minus 2.0 t, and y2 equals 4.0 times the sine of 3.0 x plus 2.0 t. By combining them, the standing wave equation becomes y equals 8.0 times the sine of 3.0 x multiplied by the cosine of 2.0 t. If we want to find the maximum displacement at a specific point, like x equals 2.3 centimeters, we calculate 8.0 times the sine of 6.9 radians, which gives us approximately 4.6 centimeters. We can also determine the wavelength by using the wave number k, which is 3.0. Since k equals 2 pi divided by the wavelength is 2 pi divided by 3.0. This allows us to locate nodes at any position x, that is a multiple of pi divided by 3.0. In summary, standing waves are the result of the superposition of two identical waves moving in opposite directions. The resulting wave function, y equals 2 times the amplitude times the sine of kx times the cosine of omega t, confirms that this is not a traveling wave because the spatial and temporal variables are separated. Every single element of the medium undergoes simple harmonic motion at the same frequency, but their amplitudes vary based on position. Nodes remain perfectly stationary with zero amplitude, while antinodes reach the maximum possible displacement of 2 times the original amplitude. This creates a stable, oscillating pattern rather than a pulse that moves through space. To wrap up our discussion, consider these review questions to test your understanding. First, think about the mathematical form of the resultant wave function. Why does the fact that it is not a function of the quantity kx minus omega t mean it fails to represent a traveling wave? Second, consider the physical dimensions of the pattern. If we were to double the frequency of the two traveling waves that create the pattern, how would that change the physical distance measured between two adjacent nodes? Reflecting on the relationship between frequency, wavelength, and the node position formula will help you find the answer.